Beyond the reach of traditional microscopes and within theoretical physics lies a frontier not so much of remoteness as a possibility in understanding. This frontier is challenged not by physical barriers or vast distances but by the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the building blocks of technology and reality behave quite differently from anything we've ever encountered in our macroscopic world. Quantum mechanics is a phrase that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in several places at once, they can spin in opposite directions at the same time, they can be entangled in the vastness of space, acting in concert with no apparent connection. These bizarre behaviors are at the heart of a technology that could revolutionize our world, quantum computing. At the heart of this technological storm lies a concept so revolutionary and yet so elusive that it challenges our very perception of information and reality. By traveling the quantum frontier, we enter a space where information is not just processed but exists in states that defy classical logic. Here, quantum bits, or qubits, can store many possibilities at once compared to the simple bits of today's digital devices. But how to preserve information in a system that loses its essence at the slightest interaction with the environment? Scientists may have some answers to that question because quantum mechanics does more than just redefine computing, it encourages us to rethink the cosmos, intertwining with the fabric of space and time and enigmatic phenomena such as black holes. These cosmic anomalies are not mere objects but the key to understanding the quantum puzzles that hold the secrets of the universe's information storage and retrieval systems. Join us on our expedition, an expedition to the frontier of quantum mechanics, an exploration that may ultimately redefine the meaning of computing, data protection, curing disease, and perhaps understanding the very fabric of reality itself. So, you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, where data is processed as a straight series of zeros and ones. In contrast, quantum computing works with qubits, which can embody zeros, ones, or both at the same time, utilizing special properties of quantum mechanics to perform complex computations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in developing quantum computers is creating and maintaining quantum memory. Unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause quantum information, known as quantum states, to decohere, that is, erase the stored data. It's like trying to hold a spinning coin on its edge. This susceptibility stems from the fundamental nature of quantum memory. It is not simply a matter of storing data but of preserving complex quantum states, which are the basis of the potential of quantum computing. Herein lies the paradox at the heart of quantum computing, the no-cloning theorem. This theorem is a unique rule of the quantum world and states that it is impossible to create an exact copy of an unknown quantum state. In the everyday world, if you want to prevent data loss, you can make copies of it. But in quantum computing, it's impossible to make an exact copy of a qubit containing unknown information. This poses a serious obstacle because it means that traditional methods of data protection and error correction, like backups, simply don't work in the quantum domain. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They are using quantum error correction techniques that involve entangling qubits, linking them together in complex ways and allowing the system to detect and correct its own errors without having to directly measure the quantum state. These methods don't just preserve information, they preserve the very essence of quantum behavior. But how can the very gravity wells where not even light can penetrate and quantum computing be related, you ask? The intriguing connection between black holes and the burgeoning field of quantum computer science begins with one deep mystery they share in common. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed groundbreaking ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma: what happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to the quantum computing problem with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So, how much information can a black hole store? Bekenstein, in turn, presented the concept that the entropy of a black hole, in fact, its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. But how can a surface store information, you may ask? After all, you need some kind of structure, you need atoms or something else that can store bits of information. It turns out you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck square units are the smallest measurable scales in the cosmos. These units, named after Max Planck, mark the limits beyond which classical theories of gravity and space begin to break down and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the most minuscule dimensions imaginable. So why is the information content of a region of space equal to the surface area surrounding that region and not its volume? Consider this analogy to better understand the unconventional way information is stored in a black hole. Imagine that your room is not just a library, but a magical library where your entire collection of books can be encoded simply on the wallpaper that covers the walls. Here, instead of measuring the volume of the room to determine how much it can hold, we look at the surface area of the walls. And this radical idea reflects how black holes store information, but not in their vast void, but on their outer surface, at the event horizon. This leads us to the holographic principle, which may seem like science fiction, but it's a serious scientific theory inspired by the thermodynamics of black holes. A hologram, colloquially speaking, is a flat surface that contains all the data needed to display a three-dimensional image. If you apply this to the universe, the startling possibility arises: everything you see around you, from your cup of coffee to the stars in the sky, could be a projection of information encoded on a distant two-dimensional surface. The Juan Maldacena model, known as the anti-de Sitter conformal field theory correspondence, or ADS CFT, goes further. It proposes that the type of universe described by Einstein's theory of gravity, negatively curved and seemingly limitless, could be equivalent to a gravity-free quantum field theory defined at the boundary of that space. Essentially, it's as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring in it. This revolutionary idea suggests that our understanding of space and time, however intuitive as it may seem, may be an emergent phenomenon from a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic data storage observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing computations impossible for a classical computer. As we move closer to mastering quantum computing, its impact on our future is becoming increasingly clear and promising. This technology doesn't just increase the speed of data processing, it expands our ability to solve problems previously thought unsolvable. Cryptography, medicine, space exploration, it's just the beginning. In the field of cryptography, quantum computing is a double-edged sword. On the one hand, it poses a significant threat to existing encryption methods. Traditional security protocols rely on the complexity of factorizing large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods can become obsolete over time, leaving data vulnerable, from your personal correspondence to access to your bank account. However, the same ability opens up the potential for quantum cryptography, which can provide a level of security that's fundamentally unbreakable. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to eavesdrop on a quantum key changes their state, thereby revealing the presence of an attacker. This method could revolutionize the transmission of sensitive information, making our data secure against even the most sophisticated attack. In medicine, the impact of quantum computing could be revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and expensive process, often taking more than a decade. Quantum computers can significantly speed up that process by predicting the properties of complex molecules and their interactions with the human body more accurately than ever before. One interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung, allowing researchers to observe how drugs would interact with human tissue in real time. Imagine a world in which we can model the human body in minute detail on quantum computers, creating digital twins that doctors could use to test treatments tailored to each patient. This approach could not only speed up the development of new drugs but also improve their efficacy and safety many times over. It represents a shift towards more personalized medicine, where treatments are optimized for each patient's unique genetic characteristics. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across sectors. Its ability to solve complex logistical problems and optimize systems can lead to more efficient use of resources. For example, quantum algorithms have already improved cargo movement at the port of Los Angeles, increasing throughput and reducing energy consumption. Space exploration can also benefit greatly from quantum computing. Navigating vast expanses of space requires processing vast amounts of data for trajectory alignment, system diagnostics, and life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation and preserving critical satellite infrastructure. Research into black holes and quantum mechanics is not just a theoretical fancy, it's shaping the very tools we expect to revolutionize our future. The insights gained from studying these cosmic mysteries are helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research into the uncharted reaches of the cosmos. So, quanta, in simple terms, are the smallest possible units of any physical property involved in an interaction, such as energy or matter, such as particles and photons. In classical physics, everything seems smooth and continuous, but at the quantum level, things like energy move in tiny discrete packets, such as quanta. That's why there are quite a few different methods of quantum computing, each exploring unique approaches to using these tiny units to generate enormous computing power. One of the leading techniques in current quantum computing research involves superconducting circuits. Companies like Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures near absolute zero, allowing quantum states to persist long enough to perform complex computations. Another well-known method uses trapped ions as qubits. Companies like IonQ and Quantinuum use this technique, where ions are held in space using electromagnetic fields and manipulated with lasers to perform quantum operations. This method boasts longer coherence times, meaning that quantum states remain stable for longer periods, although the speed of operation is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum, with qubits encoded using photons, particles of light. This approach, promoted by companies such as Xanadu and startups affiliated with academic groups, operates at room temperature and uses the properties of light to perform quantum computing. Recent advances include Xanadu's development of the Borealis chip, which uses a novel method of manipulating groups of photons to gain quantum advantages. In turn, topological quantum computing, which has emerged from a more theoretical framework, offers a new approach to utilizing quasiparticles, particles that arise from interactions within a material. Microsoft has been a key player in this field, exploring ways to create and manipulate these quasiparticles to create qubits that are naturally immune to external perturbations, potentially solving the problem of quantum decoherence. In addition, one quite revolutionary approach to quantum computing is rapidly gaining momentum. This new method, using atoms held in optical tweezers, represents a significant leap forward in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative technology and learn how it has the potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are nothing new in physics, but their application in quantum computing is a new and rapidly developing frontier. By using lasers to capture individual atoms, scientists create qubits that are less susceptible to interference and easier to control than traditional methods. This technique is based on the unique properties of atoms, being small and electrically neutral, they naturally avoid mutual interference that affects other types of quantum bits. This reduction in noise and interference is crucial to maintaining the coherence of quantum information, which is an ongoing challenge in quantum computing. A recent breakthrough in February this year involved the use of microlens arrays, which allow a significant increase in the number of atoms that can be manipulated simultaneously. These arrays allow thousands of atoms to be precisely arranged in regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange more than 1,000 atoms with remarkable precision. These atoms are not just statically held, they are dynamically controlled, ready to perform complex quantum operations. The term, supercharging, accurately describes the improvement this method brings to quantum computing. By aligning two layers of microlens arrays and superimposing laser traps on them, scientists create a dense grid of atomic qubits. This arrangement not only increases the initial number of qubits but also improves their overall stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows each qubit to be individually addressed and manipulated, opening the way to complex and large-scale quantum algorithms that were previously unattainable. When this new method is compared to existing technologies like superconducting qubits and ion traps, the atoms in tweezers approach offers significant advantages in scalability and error reduction. Its ability to scale rapidly to thousands of qubits makes it a formidable competitor to better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation but a very realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing complex problems from cryptography to material science to be solved. As we conclude our journey through the quantum frontier, we find ourselves at a pivotal moment where quantum computing is moving from theoretical research to practical applications. The SPRIZE Quantum Applications Competition epitomizes this transition, presenting a challenge with a significant $5 million incentive to spur innovations that apply quantum computing to real-world problems. Over the next 3 years, teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, material science, energy, and other fields. This initiative not only accelerates the development of quantum technologies but also emphasizes the potential of quantum computing to solve humanity's most pressing problems. By pushing the boundaries of quantum computer capabilities, SPRIZE aims to stimulate the transition from experimental quantum applications to everyday tools, making the fields of quantum mechanics accessible and useful to society at large. Imagine being able to harness the power of the sun, which has been the lifeblood of our planet for billions of years. Its energy, produced in a process known as fusion, illuminates our world and sustains life. But what if we could replicate this process right here on Earth? What if we could create our own miniature suns to power our homes, our cities, and our world? Sounds like science fiction, doesn't it? But what if we told you that this is not a distant dream, but a reality that scientists have been approaching for decades? In the heart of California, at the Lawrence Livermore National Laboratory, a group of dedicated scientists work tirelessly on this mission. Their goal, to accomplish nuclear fusion, a feat that could revolutionize the way energy is produced and pave the way for a future of clean, limitless power. Quite recently, at the end of last year, there was a breakthrough that could have changed everything, illuminating our future. Imagine our star, the Sun, 93 million miles away in the vast expanse of space. It is a giant, glowing ball of gas that's incredibly hot. Have you ever wondered what makes the sun shine so bright? The answer is both simple and complex: nuclear fusion. In simple terms, nuclear fusion is the process by which two light atoms combine to form a heavier atom. It's like taking two small Lego blocks and putting them together to make a bigger one. There's a catch: when these atoms combine, they release a huge amount of energy. They release so much energy that it allows this energy to power the sun and make it shine. Now, you may be thinking, that sounds great, but what does that have to do with us here on Earth? Well, if we could replicate this process, we could potentially create a virtually limitless source of clean energy. Imagine your house, your city, and even your car being powered by the same process as the sun. That is what fusion promises us. But this idea is not new at all. Scientists have been dreaming of harnessing the power of fusion for decades. In fact, the concept of nuclear fusion was first introduced in the early 20th century by physicists like Albert Einstein and Hans Bethe. Over the years, there have been many attempts to achieve fusion, from Project Sherwood in the 1950s to the first tokamaks in the 1960s, and the construction of modern facilities such as ITER and the National Ignition Facility in the US. Each of these efforts brought us closer to the goal of achieving fusion. Although there have been problems and setbacks along the way, the dream of harnessing star power has never faded. Now, with the recent breakthrough at Lawrence Livermore National Laboratory, we may be closer than ever to making that dream a reality. Just imagine a world in which the light in every house, street, and city is powered not by coal or gas but by the same process as the stars. As we discussed earlier, fusion is a process in which two light atoms combine to form a heavier atom, releasing huge amounts of energy. But what makes the process so special? Why are scientists around the world so interested in it? Today, most of our electricity comes from burning fossil fuels like coal and gas. These processes release harmful greenhouse gases into the atmosphere, contributing to climate change. Such resources are also finite, which means they will run out sooner or later. But fusion offers another way. Fusion is fueled by hydrogen isotopes such as deuterium and tritium. Deuterium can be extracted from seawater and tritium from lithium, which is abundant in the Earth's crust. This means that the fuel for fusion is almost limitless. And remember, the energy released by fusion is enormous. Just 1 gram of fusion fuel can produce the same amount of energy as 8,000 gallons of gasoline. That's like driving around the Earth more than 300 times. Fusion could generate huge amounts of energy without the carbon emissions associated with fossil fuels. This could help us fight climate change and move towards a more sustainable future. The outlook for fusion energy extends beyond the scientific community. Political figures, such as U.S. Senate Majority Leader Charles Schumer, also recognize its potential. He stated, "This breakthrough is a giant leap toward making fusion power a reality. It marks the beginning of a new era in energy production that is cleaner and virtually limitless. The potential for our economy and the environment is enormous." With the stakes so high, it's not surprising that the fusion race is often compared to the space race of the 20th century. But achieving nuclear fusion is not easy. It requires incredibly high temperatures and pressures, such as those found in the heart of the Sun. Also, for many years, the energy required to start a fusion reaction exceeded the energy it produced. But this is where the Lawrence Livermore National Laboratory and the National Ignition Facility come into play. They are working to make fusion a reality, and their recent breakthrough could be a game-changer. Imagine a place where the world's brightest minds come together to solve some of the biggest problems facing humanity. That place is the Lawrence Livermore National Laboratory, or LLNL for short. Located in California, LLNL is a center for scientific and technological innovation. It is home to thousands of scientists, engineers, and other professionals who work on a wide range of projects, from national security to environmental science to, you guessed it, fusion. One of the gems of LLNL is the National Ignition Facility, or NIF. This is where the magic of fusion happens. NIF is the largest and most powerful laser facility ever built. It is the size of 3 soccer fields and contains 192 laser beams that can transmit more than 2 million joules of energy. 2 million joules is about the kinetic energy of a car driving down an expressway. So imagine the energy of a car rushing down a highway concentrated at a tiny point in a split second. That's the kind of energy we're talking about when the National Ignition Facility's lasers go off. But what exactly does the NIF do? Its main task is to create extreme states of matter, like those found in the cores of stars or inside nuclear weapons. It does this by focusing its 192 laser beams on a tiny target, creating temperatures and pressures that are several times higher than those at the center of the Sun. The target is a tiny capsule filled with fusion fuel, which is a mixture of hydrogen isotopes, deuterium, and tritium. When the lasers strike the target, they detonate the fuel, triggering a fusion reaction. But the road to this point was far from easy. As LLNL Director Dr. Kim Boudil says, the quest to ignite fusion in the laboratory is one of the most significant scientific challenges ever undertaken by humankind, and its achievement is a triumph of science, technology, and above all, people. Overcoming this threshold is a vision that's led to 60 years of focused inquiry, a continuous process of learning, building up, expanding knowledge and capabilities, and then finding ways to overcome new problems that arise. These are the problems for which U.S. national laboratories were created. NIF is a marvel of modern technology and science, and it's played an important role in advancing our understanding of nuclear fusion. But it's not just about science. The work being done at NIF may one day lead to a world powered by clean, abundant fusion energy. So how did scientists achieve these results? Let's delve into the details of the achievement and how it brings us one step closer to such a future. In December 2022, something extraordinary happened at the National Ignition Center. For the first time, a man-made device achieved a fusion reaction that produced more energy than was consumed. This is known as fusion ignition, and it's really important. But what exactly does fusion ignition mean? Remember how we talked about fusion like connecting two small Lego blocks to make one bigger one? Fusion ignition is similar to that, but with a twist. Instead of just joining two blocks together, you join so many blocks that the energy release starts a chain reaction, causing more and more blocks to join together on their own. It's like lining up a row of dominoes and knocking over the first one. That first knock knocks over the second, which knocks over the third, and so on until all the dominoes fall. Well, that's exactly what happened in the NIF experiment. The energy from the lasers triggered a thermonuclear reaction that continued on its own, releasing more energy than it took to trigger it. But achieving this has not been easy. As Dr. Aroti Prabhakar, Chief Science and Technology Advisor to the President, says, "We have had a theoretical understanding of fusion for more than a century, but the road from knowledge to action can be long and difficult. Today's milestone shows what we can do with persistence." Once again, as the sun sets, we're left to wonder, what if we could harness the power of the stars to light our cities, power our homes, and grow our industries? But what would a world powered by fusion energy look like? First, fusion energy is clean. Unlike fossil fuels, it produces no greenhouse gases or harmful pollutants. This means it could play a crucial role in combating climate change and improving air quality. In addition, fusion energy is safe. There's no risk of meltdown as in a nuclear fission reactor, and it produces no long-lived radioactive waste. In the event of a malfunction, the reaction simply stops. We have an enormous supply of fusion energy. The fuel for fusion is water and lithium, which are in abundance on Earth. This means that fusion energy can provide a virtually unlimited supply of energy, reducing our dependence on limited resources like oil and gas. But while the potential benefits of fusion energy are enormous, there are still many problems to be solved. Fusion reactions require extreme conditions that are difficult to achieve and maintain, and the technology to capture and convert fusion reaction energy into usable electricity is still in the early stages of development. However, the event itself gives us grounds for optimism. It shows that fusion ignition is possible and that we are on the right track. Thanks to continuous research and development, the dream of a world powered by fusion energy can become reality. But what does the future hold for fusion energy? Although the recent achievement of fusion ignition is a milestone, it's only the beginning. There's still a long way to go before fusion energy can be used on large scales to power our homes, cities, and industries. Future research will focus on several key areas. First, maintaining the extreme conditions required for fusion reactions is a major challenge. Second, we need to develop the technology to capture and convert fusion energy into usable electricity. Finally, the economic feasibility of fusion energy is an important consideration. Building and operating fusion reactors can be very expensive, and it's necessary to develop cost-effective solutions to make fusion energy accessible and affordable. But despite these challenges, the future looks bright. As Dr. Budil of LLNL says, achieving fusion ignition in the laboratory is one of the most important scientific challenges ever undertaken by humankind, and overcoming it is a triumph of science, technology, and above all, people. With continued research and development, we're on the verge of a new era in energy production. Imagine a future where fusion reactors power our homes, cities, and industries. Where electric cars are charged by the same process that powers the sun. where we no longer have to worry about running out of fuel or the harmful effects of burning fossil fuels. This is the future that fusion energy promises us, a future where clean, limitless energy powers our world. So, the next time you look up at the sky and see the sun shining brightly, remember that deep within its core, a powerful reaction is taking place, creating enormous energy. And remember that here on Earth, scientists are working tirelessly to harness that same power for the benefit of all humankind. With the recent breakthrough at the Lawrence Livermore National Laboratory, we're one step closer to a future where the power of the stars lights our cities and powers our world. The universe seemed mutually inconsistent, and there was no consensus on the composition of the energy density of the universe. The model successfully announced a wide range of astronomical phenomena, from the large-scale structure of the cosmos to anisotropy in the cosmic microwave background. Despite the complexity of the universe, the lambda cold dark matter model is relatively simple and characterized by a small set of parameters. These include the Hubble constant, the densities of dark matter and dark energy, and the initial conditions for the existence of the universe. The predictive power of the model allows astronomers to test its validity with observations such as the distribution of galaxies and the cosmic microwave background. The Dark Energy Spectroscopic Instrument has provided new insights into the mysterious nature of dark energy. By analyzing more than 6 million extragalactic objects at vast cosmic distances and different epochs, DESI provides reliable measurements of the expansion history of the universe with previously unattainable precision. This extensive data set, covering a redshift range from 0.1 to 4.2, allows us to reconstruct the expansion of the universe in detail and reveal the influence of dark energy throughout cosmic time. One of the most intriguing results from the first year of DESI observations is the indication that dark energy may not be a static force but may evolve. This hypothesis stems from the subtle discrepancies observed between DESI measurements and the predictions of the lambda cold dark matter model. In particular, the data collected in this study suggests that the parameter of the dark energy equation of state is close to being consistent with the cosmological constant. However, if we extend the lambda model and add a time-varying dark energy equation of state, the DESI data, in combination with the cosmic microwave background or type Ia supernova, definitely indicate a departure from the model. This means that the influence of dark energy may not be constant but may change with time. This preference persists in different combinations of data sets, indicating deviations from the lambda model. The data obtained in the survey, especially the discovery of dark energy, poses a serious challenge to the lambda model traditionally based on the representation of dark energy as a constant component. The detailed mapping of the cosmic expansion history with the instrument provides data that may require modifications to the standard cosmological scheme. In particular, the parameters present-day value and rate of change of the dark energy, indicating the variation of the dark energy influence with time, indicate a deviation from the static lambda assumption of dark energy represented by the cosmological constant lambda, which requires a critical reassessment of the model's functions. The results of the paper have profound implications. If the dark energy equation of state does indeed change, this could lead to a major revision of our ideas about the expansion of the universe and its ultimate fate. Such a paradigm shift will not only refine our understanding of dark energy but would also affect the broader cosmological models that describe the composition, structure, and evolution of the universe. To integrate these ideas, cosmologists may need to explore new theoretical frameworks or improve existing models to account for the time-varying dark energy component. This may require developing more sophisticated models that account for the dynamical behavior of dark energy or revising our understanding of the interactions between dark energy, dark matter, and other cosmological parameters. One intriguing alternative is quintessence, a dynamic form of dark energy with a changing equation of state. Unlike the cosmological constant lambda, which remains constant throughout cosmic time, quintessence is a field that evolves, potentially providing clues to the observed divergence. Could the changing nature of dark energy be a manifestation of quintessence? This model allows the effects of dark energy to vary, potentially consistent with the evolving equation of the state of dark energy hinted at by the study. The possibility that dark energy interacts with dark matter or other components of the universe also opens up an exciting paradigm. Such an interaction could lead to observable effects on cosmic scales, potentially explaining the changing equation of the state of dark energy. Another intriguing but radical proposal is the concept of early dark energy. This model suggests that dark energy played an important role not only in the late universe but also in its early stages, leaving imprints on the anisotropy of the cosmic microwave background and large-scale structures. This may offer a new lens through which to interpret the findings, especially if dark energy effects have been woven into the fabric of the cosmos since its dawn. The viability of each of these theories depends on consistency with observational data at various scales, from CMB anisotropies to galaxy clustering and supernova luminosity distances. The contribution of the project lays the foundation for future research in cosmology. As DESI continues to produce an unprecedentedly detailed map of the cosmic web during its 5-year mission, it's expected to inspire several future projects aimed at delving deeper into cosmological mysteries. These future projects will likely build on DESI's findings, utilizing advanced observational techniques and theoretical models to further explore dark energy and its impact on the cosmos. A discussion between study participants Shashad Nand and Andrew Font-Rera emphasized the collaborative nature of this research, emphasizing the integration of DESI data with other observations to create a more complete picture of the evolution of the universe. Such a collaborative approach is essential to deepen our understanding of dark energy and its role in shaping the ultimate fate of the universe. Although the instrument results challenge our current cosmological models, DESI's journey is far from over. It is merely a prologue to a much larger cosmological narrative. And standing at this threshold, we remind ourselves of how much we still have to learn about the structure of the universe. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering but also of ambition and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined, thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics, it's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These black holes, although tiny and harmless, can provide evidence of extra dimensions and help us understand the true nature of gravity. Thus, by trying to open these portals, physicists are not looking to send anyone to another universe. They seek to understand whether our universe is part of a much larger, more complex reality. In the control room of the Large Hadron Collider, a dense atmosphere filled with anticipation and focus reigns. This is where scientists and engineers control experiments in real time, monitoring countless parameters to ensure optimal performance. The room is filled with displays, each showing different aspects of the collider's operation, from the state of the beams to the results of the collisions. The process of initiating a collision begins with the injection of protons into the collider, which then accelerates them to incredible speeds using a series of increasingly powerful electric fields. These protons, traveling at nearly the speed of light, are guided by powerful magnets that bend and focus the beams until they are forced to collide with each other. At the moment of collision, the energy involved is immense. The beams, concentrated into a minuscule point, reach temperatures more than 100,000 times hotter than the center of the Sun. The particles inside the beam interact at such high energies that the resulting collisions create conditions that have not existed since the early moments of the universe. As the protons collide, they break apart, and new particles are created from the energy of the collision. These particles are detected by giant detectors surrounding the collision points, each designed to capture different aspects of the interactions. Detectors, some the size of a multi-story building, are incredibly complex devices consisting of millions of sensors and intricate electronics. They record data at astonishing rates, capturing snapshots of particles flying in all directions. This data, equivalent to the information in millions of CDS, is then processed and analyzed by powerful computers, allowing scientists to sift through the data and look for signs of new physics. The significance of these collisions cannot be overstated. Each one offers a fleeting glimpse into the fundamental processes that govern our universe. They give us the ability to probe deeper into the mysteries of dark matter, dark energy, and the origins of mass. Moreover, by studying these collisions, we are expanding our understanding of the fundamental laws of nature and moving toward a more complete picture of the universe's origin and structure. However, the technological challenges of operating such a machine are immense. The LHC operates at near absolute zero temperatures to maintain the superconducting magnets that bend and focus the particle beams. The complexity of the systems involved, from cryogenics to beam dynamics, requires careful monitoring and constant adjustments. This task falls to a dedicated team of engineers and scientists who ensure that the collider operates smoothly and safely. The diversity of skills and expertise required to run the Large Hadron Collider underscores the global nature of the project. From mechanical engineers to data analysts, the collaboration brings together some of the brightest minds in the world, working towards a common goal, unlocking the mysteries of the universe. The results obtained from these collisions are not only significant for particle physics. They also have far-reaching implications for our understanding of the cosmos. The data collected from the LHC experiments can help answer fundamental questions about the nature of matter, the forces that shape our universe, and the possible existence of other dimensions. In the face of such profound scientific research, it's easy to understand why the Large Hadron Collider captures the imagination. It represents the pinnacle of human ingenuity and ambition, a testament to our desire to explore the unknown and expand the frontiers of knowledge. As we continue to delve deeper into the fundamental nature of the universe, we can only speculate about the discoveries that await us and how they will transform our understanding of reality.